So this final lecture is about, so we talked all about different ways of acquiring three-dimensional information, right? So just as a refresher, first we talked about LiDAR scanning, and a little side note on things like time-of-flight cameras, like what's inside the new Microsoft Kinect. Then we talked about structured light scanning, which is basically, you're pushing light stripes or dots into the scene to be able to, acquire shape by watching how that stripe deforms. And then we talked about multi-view stereo, right, which is basically passively looking at many images of the same environment and using basically a combination of structure for motion with dense correspondence to populate the world with 3D textured points, right? And so now I'm going to kind of step back and say, okay, so we talked about several different modalities for acquiring 3D data. No, do not allow. And we now want to know, okay, so how do we deal with multiple instances of this data put together? So one thing that happens all the time, especially with something like a LiDAR scan, is that you have one 3D point cloud from this perspective, another 3D point cloud from some other perspective, and you need to know how do they fit together to be able to make a larger map or a larger 3D impression of the world, right? So in some situations, like for example, we talked about in structured light scanning, you have some sort of either super calibrated system or you've got some sort of like a, almost like a motion capture kind of system that kind of tells you how you should align these scans together. But in many situations like LiDAR, you really don't know where that scanner is, and you have to figure out how to put these points in the same coordinate system. So that process is called registration. And so we talked about kind of features and registration in the context of 2D images, right? We talked about, Harris corners and Sift features, and then how do you use those to estimate transformation, like either a parametric transformation, like a projective transformation, when you've got two images of a plane or when the camera is not translating. Or we also talked about things like scatter data interpolation. So once you've got these correspondences, how do you estimate, transformations? So we have analogous problems in 3D, but both the process of finding features and the process of what is that transformation and how do two scans match up, they're very different in our world here. And so, so mostly what I'm going to talk about here is motivated in the context of LiDAR scanning, when you've got these kind of unorganized point clouds and you don't know where the scanner was that took the point clouds and you want to put them together into a bigger picture. And so the first problem you have to come up with a solution to is 3D feature detection, right? So feature detection in 3D is actually a lot more challenging than in 2D because, again, if you think back to what the actual source of the LiDAR data is, it's just a bunch of 3D points out in space. And if you zoom in on those points, it's pretty grungy, right? Whereas if, so one thing you can do is you can triangulate the mesh. So you can say, okay, since the LiDAR scanner is producing points in a fixed order that comes from this little dot skipping across the scene, you kind of know that some points are neighbors of other points, and you can say, okay, I can connect up neighbors of points into little quads or little triangles, and as long as the distance between two adjacent points is not too high, then that tells me where I can make my edges. And so, for example, when I have places like this where I have missing data, you probably know that you don't want to bridge the gap between a point here and a point way over on the other side of the window. So when you're using 3D images, you're kind of stuck with having to extract features from this type of data, right? And so the first thing I want to talk about is exactly this problem, but definitely life is much easier when you not only have the points, but you have some sort of a co-registered color image that goes along with the points, right? So we talked about how, for example, the LiDAR scanner that we have on campus produces a co-registered image that lets me texture that point cloud with realistic colors, right? And so when you've got both an image and the points, life becomes a little bit easier. But when you just have the points alone, there are a couple of well-known 3D kind of descriptor algorithms, right? So the first thing I want to say is that surprisingly, there aren't a lot of very reliable or robust 3D detector algorithms, right? So like Sift, for example, in 2D is a way of choosing good feature points, right? Or Harris corners even. We know that those are feature points that are going to be kind of reliably easy to track or to find again in images of the same scene. You might imagine that when you're faced with data like this, you could do something kind of similar. You could kind of say, okay, I want to find, like a point on the wall here is probably a bad feature. A point on this window here where there's lots of texture and edges is a good feature. And there have been attempts to extend things like Harris corners, for example, to 3D data. But surprisingly, there's not actually a lot of very robust 3D feature point detection algorithms. What happens actually instead in practice is that you choose almost randomly a bunch of points in the 3D scene, and then you construct what are called 3D descriptors around those points, and then you try and find those descriptors again in another scan at the same place. And so it's definitely a little bit more seat of the pants than 2D feature matching. And I'll show you our solution to that problem in just a second. So here's the original data. And so the first kind of well-known way of doing 3D descriptors is called a spin image. And so the idea is that suppose that I want to build a 3D descriptor around this red point on this chicken. Okay. So what I do is I take this point here, I centered it on the red point, and then what I have to do is estimate the normal to the surface at the points that I care about, right? And normals are not really, hopefully, in well-behaved 3D scans, not too hard to estimate. For example, if you're able to mesh up the surface like this, you can estimate 3D normals by just saying, okay, I'm going to look at the average of the normals of all the triangles that meet at my point, or I'm going to fit a little surface to all the points that were within a few millimeters of my point, put a plane on that surface fit, and then use the normal to that plane as my normal to the point. So what you do is you say, okay, I'm going to align this cylinder on top of the point, and I'm going to have the normal of this cylinder pointing outwards from the surface. Okay, so if you imagine there's a little cylinder on the surface of this chicken pointing outwards, right? And then what you do is you have an aggregation of how many points on the surface fall into each of these bins. And in this case, the bins are like cylindrical bins. So here you can see like the first bin has, is like a little narrow cylinder, and it's sampled kind of evenly along the up and down direction, and then kind of evenly in the radial direction. So you can say, okay, how many points fall within this cylinder? How many points fall within this kind of ring, like this solid ring with a middle taken out? How many points fall within this larger one? And how many points fall within this larger one? So basically what you have is kind of like a histogram where one axis is how far am I in the up and down direction, that's the normal direction, and then one axis is how far am I in the radial direction. And then the idea is, now suppose I saw this chicken from another perspective and it was like rotated in 3D space, right? So what I could do is I could build a spin image again, and because these, the idea is that if I can find a point and if I can reliably estimate its normal again, then I should get basically the same spin image when I put the cylinder on top of the chicken. One reason that the reason this is called a spin image in the first place is that you'll notice that I would get the same descriptor if I kind of spun the cylinder around its axis, right? And the reason that I like to do that is that it can be difficult to estimate an accurate, so let me just go to my paper for a second. So kind of the difficulty is, I take my surface, I have my point, I put my cylinder on top of that point. In practice, the cylinder is much larger than this. This is just like one bin of the cylinder, right? And so the idea is that, you could say, okay, well, instead of having a situation like this where I have just, these annular bins, I could kind of chop up these bins into different angles. But to do that really robustly, I would need to have a sense of how do I orient like the up-down axes. So I know what this axis is. This axis is the normal. But estimating these two axes on the surface robustly is really tricky, right? Because those can get, you can have noise on the surface of the object that will definitely corrupt my kind of XY plane if I were to try and build something on the tangent plane of the surface, right? So, for example, you might imagine, okay, what I could do is I could take a point and I could try and estimate a plane here, and I could say, okay, the x-axis points in the direction of the biggest gradient, and the y-axis points in the opposite direction, and this is the normal to the surface. But all I'm trying to say is that these two axes are difficult to estimate robustly, and so in practice, that's why we use spin images. Is all we have to do is estimate the normal robustly, and that's pretty easy to do. And so, again, the idea behind spin images is that I would take, a bunch of spin images from one 3D scan and a bunch of spin images from another 3D scan, and I would basically try and match those descriptors. And And then if I can find a few that really match well, those 3D correspondences provide the seed for a subsequent registration algorithm. Okay. Yeah.
My question is actually right in that sort of estimation of the main gradient. How do you then decide where you start the spin image, or do you just have to compare the spin image, against itself in all types of terms?
Yeah, I mean, basically, so you don't have to compare the spin image. So comparing spin images against themselves, there's never any ambiguity about the comparison because there's no need to, because the spin image kind of spins freely around this uncertainty, there's no need to try and estimate that tangent plane robustly. But kind of what I was trying to get at earlier is that there's no good way to pick the 3D points in scan 1 and scan 2 for which I compute the spin images. And so in practice, at least in the early days, what they would do is they would compute, okay, lots of spin images here, lots of spin images here, and just find the ones that matched up the best in the hopes of getting a few correspondences that you could latch onto. And once you've got a few good ones, then you can kind of pull the scans together. I'll show an example of that after I talk about the features.
I'm more thinking about like what you were talking about
Yeah.
just a second ago with
Yeah.
estimating the general direction of a particular spin image on,
Right.
on a horizontal axis or
Right.
something like that. Because then that decides where you start your spin image, right?
So, I see. Well, you always start the spin image centered on the point. So this is like the point on the surface, right? And I go a couple bins above and I go a couple bins below the surface, right?
Right.
So I don't have to worry about the spin image sliding up and down this axis.
So let's say on this red image here,
Yeah.
the radial,
The red image.
you have the top boundary
Mhm.
and the bottom boundary R1. Is that kind of
R1.
We're rotating around the normal, which is the x-axis that we're looking at here.
We're rotating around the I would say this is the z-axis, but okay.
Okay,
Yeah.
sure. So the normal is the z-axis,
Mhm.
and we're rotating around that.
Yep.
Right. Where do we decide at what theta do we start rotating to get that image?
At what theta do we start rotating at that image?
Like essentially, how do you decide the upper and lower boundaries where that falls? Because it seems like this image can be translated any number of ways up and down and sheared on the other side, and it would be the same spin image.
Oh, well, so maybe I explained this wrong. So if you think about this, like there is no theta in this spin image, right? So what I have here is, like for example, let's suppose, I wish I could draw on my screen here. I guess I could, but it's too late for me to figure out how to do it. So let's suppose I'm talking about like this coordinate here. So it's like saying I go this far away from my point in the normal direction, and then I go this far over in the radial direction. So let's say that puts me in this bin, right? And then what I do is I aggregate, like a histogram, all the 3D points of the scan that fall within this kind of solid ring, right? And so I'm basically adding up any point that is in that ring for any theta, right?
Okay.
So then I've removed the dependence on theta because I'm just adding up everything in that solid chunk, right? And no matter if I were to rotate that, I would still be adding up exactly the same points, right? So the idea is the histogram is kind of orientation robust, right? That's the idea.
All right.
Does that make sense?
It does.
Okay.
That clarifies it.
Good, good. Other questions? So this is one very well-known 3D descriptor. Another well-known one is called shape contexts, which is kind of similar, although hard to illustrate. The idea is that instead of using a cylindrical kind of set of bins, I use sections of a sphere. And so I have, again, an estimate of the point on the surface. I have the 3D normal to that point. And then what I do is I center this sphere on that point, and then I aggregate which points are falling within each kind of sector of the sphere. Now this one does have a angular dependence because the sectors of the sphere are spaced out with units of theta. And so in this case, kind of to address the question that was asked earlier, what you'd have to do is if I wanted to match one shape context for one image to another one, what I would kind of do is I would try and estimate it for all the possible click offsets of theta, right? So I'd say, okay, what if this bin was theta equals 0? Okay, what if that bin was theta equals 0? So in this case, I have to actually compare all the possibilities, right?
And you could potentially calculate a dominant direction to use that.
Yeah, I mean, you could try to so exactly. You could try to compute, again, like the dominant direction on the tangent plane and try and make that theta equals 0. But that part, like I said, is in practice a little bit tricky to try and do because of noise and because of sampling errors and stuff like that. So, so life is much easier when you can also lay a image onto these points to color them, right? So this is not a color image, but what you would do is you say, okay, I know where the scanner, I know I can put this image in 3D space in the right position in front of the scanner, and then I can push the colors of this image onto the surface of the object. And we showed an example of that when I first started talking about LiDAR, right? We went from this kind of gray building to a colored building, right? And then life is better, because what you could do is you can apply lots of ideas from image features to the 3D world. And actually, of all the things I've talked about in class, this is like the one thing that I actually published some papers on. Everything else has kind of been just like hobbyism. But the idea behind that is basically saying, okay, what you could do is, for example, you could take, you could find a good feature point in the image. You could push that feature point onto the mesh of the scan. You build like a little 4x4, grid of points on the tangent plane of the scan out here. Then you project that grid back down here, and you kind of make a Sift descriptor that is kind of mediated by the 3D surface. And so the idea is that, you're using image points over here, but the shape of the grid that you aggregate for the Sift bins is not just a set of squares. The set of squares is warped based on how that set appears in 3D space. And so we call this a back-projected Sift descriptor. And so then, life is much better for kind of evidence for matching, right? So it's a lot easier to match these kinds of descriptors because you inherit all the good stuff from Sift, plus you don't have to worry about just looking at random untextured 3D points. You've actually got these image textures. One thing that I think was even more successful was something we called physical scale key points. And I'm not sure I have this stored on my computer. Let's see if it's still here. Right, so this is another paper we wrote that kind of shows how grungy some of this 3D key point detection would be. So this is kind of one of the problems that we could have with the approach earlier. So what you're seeing here is on the left-hand side, I believe, I'm sorry, on the bottom is basically the idea behind what I was talking about, this back-projected Sift. And so the idea would be that I take a point in this image, I project it over onto the building, and I project it back down, and these little green arrows are the kind of sizes of the stuff that's in every Sift bin. But the problem with this is that it's possible, because your image doesn't know any better, it's possible that some of these good correspondences could be on the edges of objects. And so in this case, this is a bad place to put a descriptor, because some of these bins overlap onto some other surface of the building, like this back surface here. And so if I were to view the scene from a very different perspective, maybe I would get some of the same stuff on this surface, but I get totally different stuff over in this part of the descriptor, and that will throw off my matching. So for example, this shows that if I just kind of stupidly build these descriptors without taking into account depth discontinuities, that this would be the best match to this descriptor over here, and you can see that's like a horrible match partially because it's thrown off by the crap that shouldn't be in the descriptor. Whereas we developed what we call the physical scale key point, so that if you saw this chunk of texture from one angle, you would basically not have any contribution from things that were over the other side of the depth discontinuity, and so that when you see the same texture from a different perspective, here you can see it's different perspective and different lighting change, that the descriptor you compute here matches up with the descriptor you compute there. And so this was a nice approach to doing kind of more robust 3D matching for large-scale scenes, because we were interested at the time in kind of building-scale LiDAR scans. When you've got something that's more like a little surface on a table, a little object on a table, you don't necessarily encounter these problems as much. But when you're scanning like buildings that have like all sorts of surfaces at different depths, this kind of thing comes up a lot. And so this was one of the ideas that we had. One thing was to kind of get rid of problems with discontinuities, and the other thing, the reason that they're called physical scale key points, is that the Sift, some of the excitement about Sift was its scale and variance, right? Where you have the ability to take an image that is zoomed out and an image that's zoomed in and match them together. That's what Sift is really good at, right? But that's something that you don't need at all for 3D scans, because for a 3D scan, you're actually measuring the literal physical time of flight of something, and you get physical measurements. You know that this scan is 8 meters away, right? And so the 3D points that you have already come with a scale that is appropriate, right? So there's no need to say, how could I match this zoomed in and this zoomed out descriptor? That notion of zoomed in and zoomed out doesn't apply to 3D scans because I've got physical measurements. I may have sparser data at different at different distances, that's okay. But the point is I'm not necessarily comparing a small piece to a big piece when I'm in the 3D world. And so what we did was we basically built up, it was kind of like, without going into details, it was kind of like a LOG descriptor on the image mesh instead of on the image itself. So kind of like, this is kind of a picture illustrating the idea that you have a bunch of different scales, and just like for Sift, you have basically, you try and estimate the characteristic scale of a point by increasingly blurring the texture on the mesh. And so the idea was that things that stand out on this blurry mesh are features at a large scale, and their physical scale is in the order of tens of centimeters, whereas things that stand out on the mesh at a small scale are small scale features that are probably like, a dark brick in the midst of a sea of light bricks, that kind of thing, right? And so basically, it was kind of this 3D-ification of an LOG descriptor. And even though the descriptor that we came out with, like the one that you saw on the first page there, looks kind of like a Sift descriptor, it's not really Sift in the sense that we're not using the scale invariance. And so, these are pictures that kind of show just how grungy the matching can be once you really drill down into the data. So, like, I think we had a nice picture of the kinds of things we were matching. So, like, again, these are some scans over near biotech, and what you're seeing here is basically corresponding matches on different surfaces. Like here, this is like the bottom of a trash can or the bottom of a pillar. I guess this is a pillar, this is a trash can. And so you can see that, like, once you actually look at the little facets and points that you have in 3D data, it's really nasty to work with. I mean, it's not like the kinds of nice points that you get from looking at a color image. So, so we learned a lot about feature detection and matching on this project. Okay, so basically, again, why do you want to get these features? You want to get these features so that you can actually register the data sets, right? So you need to bring these data sets into the same frame of reference, and that process is kind of similar to, it's kind of similar to the way it does in 2D. So basically, the idea is that I start with features, and then I want to go to registration. And so let's start by just talking about registration of one scan to another. So, it's actually not that different than what you already know about. So, for example, the first time we did registration for 2D images, like for the example of the scatter data interpolation, I asked you to click on a bunch of points in one image, click on the corresponding points in the other image, and estimate the transformation, right? And then later we could say, okay, instead of clicking on those points, you use a descriptor like Sift to automatically estimate those points, right? Same idea kind of here. So the registration in 3D, in some sense, is a little bit nicer than in 2D. And that's because any scan of the same scene is related to any other scan just by a rotation and a translation, right? That's the only thing that you ever have to estimate. So any two scans are, any two 3D scans are related by an unknown, rotation and translation, right? So all you have to do is estimate these 6 parameters, right? And that is nicer than in the image case, because in the image world, images are rarely related to each other by such a low dimensional thing. For example, even when I'm looking at 2 images of a planar surface, or when the camera isn't moving and I have to estimate a projective transformation, that's still 8 parameters, and that's the simplest case, right? Whereas in most cases, 2 images are related to each other by, like, optical flow, right? Where I have basically a different motion vector for every pixel, and that's like a super high dimensional thing, right? So in some sense, the model for registration is much easier than for images, but life is a lot harder because it's harder to find and match the features. So that's kind of the trade-off. And so the most common way to register 2 scans, I mean, almost all registration scans are built upon some variant of what's called Icp, which stands for iterative closest points. And so, most registration algorithms involve Icp, which stands for iterative closest points. And so the idea here is actually really simple. And so what I do is I seesaw back and forth between two steps. The first step is, suppose I have a candidate rotation and translation. So I know that if I were to rotate and translate one scan, it would be here with respect to the other scan. So now what I do is I say, okay, one scan, let's call it, so let's call the candidate transformation P prime, and let's call the other scan Q. And so like this is like saying, this scan Q is always fixed in place, and the other scan P, we're trying to move it around to line up with Q. And so for a candidate possible transformation, what I do is I align the closest points for each point in Q to the corresponding point over in the transform scan. So that's why it's called closest points, right? So it's like saying, okay, well, this black point, what's the closest white point? It's this guy. What's the closest white point to this guy? It's over here, right? And so for every black point, I have a white point correspondence. And so, that means that some of these white points are not going to get matched up. It's possible that if you do this kind of in a kind of a not very smart way, that some black points may have, the same white point correspondence. So what I do is now I've got this set of kind of possible, correspondences, and now I've got a whole bunch of correspondences that I can use to estimate a 3D transformation. So I use those putative correspondences to re-register the scans. And so that brings me back to, a new candidate P prime that says, okay, now I've got this new rotation and translation. And I do it again. Now for every black point, I match up the closest white point and so on. And the idea is that if the two scans start out close enough together, eventually I kind of wedge them together and I get the right transformation. And so actually, this was invented kind of roughly by many people at the same time. Bessel and McKay are the ones who are generally given credit for the idea. But the idea is that they showed that if you do this seesaw between closest points and estimating the rotation and translation, eventually you reach a local minimum of the cost function of how far away these points are. And so that's a nice algorithm, and I can give just a few details on that. So basically, the first step of ICP is to find, well, actually, maybe I should write this on a different piece of paper. So the first step would basically be, for a candidate transformation, let's call that T, create T prime of P, which I'm going to call P prime, right? So basically, this is one scan, and then what I'm going to do is for every point Q in the other scan, find the closest point in P prime. So basically, what that's like saying is I find the, I guess, which point in P? Yeah. So basically what I'm doing is I'm basically trying to duplicate the same picture, right? So this is one of the scans, this is the other scan, and I find these closest things. And then the next thing is I estimate the rigid motion, which is, again, a rotation and a translation, that minimizes the sum of square distances between correspondences from step one. And then I basically iterate until convergence. And this actually seems to work pretty well. And so the kind of key question is, how do I find the initial transformation between the two scans that gives me the first set of closest points? Well, that set of correspondences basically comes from, well, that first transformation comes from something like the spin images or the shape contexts or the physical scale key points from before. So the hope is that if I can at least match 3 points out there in the world with features, that's enough to give me one initial transformation. And that's all I need to kind of go on. So that's the whole point of 3D features, is that I really only, it's not like I'm using features continuously throughout the process. What I do is I try and find a few good feature matches to seed the registration process, but then, in this case, these points are not, they're not just feature points, they're basically all the points in the scan play a role, right? So, you know, instead of just looking at the few sparse features that I'm able to grab off of these surfaces, instead, every single point in both scans is kind of pulling together the registration. And so the details of exactly how you estimate the best rigid motion are in the book. There's a nice closed form solution for this, which is nice. And there are a bunch of little twists on ICP to make things better. So basically, Icp Improvements. So to make this really work, you need to pay kind of careful attention to how this works. So one possibility is don't use all the points. You know, either subsample or get kind of a good diversity of normals. So what I mean by this last part is that, you know, suppose that I've got, you know, a wall with a little corner on it, right? And then I've got another, another image of that same wall, right? So if I'm not careful, the walls that are, you know, I guess I should draw this for the benefit of the viewers at home. So suppose I have like this and, you know, this, right? So if I'm not careful, it would be easy for my match to kind of slide along the wall surface, because all of these points will have like great registration, like there'll be like 0 registration error. What I have to worry about is that, hey, you know, what about these guys who actually are not matching very well? If I'm not careful, the stuff that's on this huge surface will overwhelm the stuff that's on this small surface. And so what I might want to do is I might want to subsample the points so that I roughly have, you know, an equal number of points for each possible normal location. And in that way, I can make sure that, you know, the little wall segment helps pull its weight in terms of pulling these things together. Another thing that you might do is, instead of matching points that are, you know, so include, let's say, include normal vectors or normal directions in matches, right? So what you want is that, you know, if I've got two surfaces like this, I should have brought a different colored pen. So it's like, okay, I'm willing to match this with this because the two normals are pretty close together, but I don't want to like match, you know, something like, you know, this normal with this normal, because those two normals are far apart, right? And so it's not going to help me make the registration any better if I'm matching points that are kind of like crazy, right? And so the idea is that I want to only use those matches that I think are going to get me closer to the solution. Another thing is, don't include points on or near scan boundaries. And so what I mean by that is that, you know, if I have, you know, one scan over here and another scan over here, right? You know, all these points over here are going to be pretty good, but at some point, you know, like if I think about what is the closest point, you know, of these guys to the other scan, I'm going to like have a bunch of matches all to the same other point on the other surface, right? And that's only going to throw me off, right? I'm not going to get anything out of that. So the idea is that I should only be kind of matching up stuff in my nice overlap region. And this is kind of important, especially when you have like partial scans. You know, this happens a lot in stuff like LiDAR scans of large scale things where you just only have a kind of a chunk of the surface, and so you don't want to match lots of stuff. You only want to match the good stuff. One very common adjustment is, instead of literally matching point to point, you match what's called the point to plane distance. And so here, what I do is, for every point in Q, I estimate the normal to the surface, and then the distance between these things is actually the white dot to the plane defined by the black point and its normal. And so this has been shown to do a better job empirically of pulling the scans together, although you do lose a little bit on the theoretical convergence of the algorithm. But it is true that in practice, this will pull the scans together more closely. And when things are aligned, these two normal directions, when things are aligned, the closest approach should basically be along this normal vector. But if it's not, this will help. Okay, and so let me just show a video of something that, again, came out of the RPI group. This is called Dual Bootstrap Icp. And so the idea here is that what you're going to see is that we started with exactly one feature correspondence, where we basically extracted our own homemade feature descriptors. We matched them up using our, I think this was probably a back-projected Sift descriptor. So that's what you see here is there's this little white ball down here that is showing where the two scans originally matched. And what you're going to see is kind of a growing rectangle or a growing colored region on these points that says which of the 3D points in each scan are participating in the matching. And so you're going to see that these scans are slowly going to kind of zipper together, and as they fuse together, the region in which the points play a role in matching expands until it covers the entire scene. So the idea is that you kind of start with a very small region of space. Oops, let me go back to this for a second. So you basically start with a local match. You do a really good job of registering within that local neighborhood, and then when you're sure you've done a great job in the local neighborhood, you expand the neighborhood to be bigger, right? And so this is kind of like saying, instead of trying to match the entire set of scans all from the get-go, you say, okay, I'm going to seed my scan match with one super good feature point, and then I'm going to make things better and better, right? And so this actually works remarkably well because we're really only using one, like literally a single feature point match to register the entire scan pair, right? Everything flows through this one good feature point match. And so in practice what we do is we say, okay, we're going to take the top 50 feature point matches, we're going to register from those starting points, and then we're going to see of those 50, which ones led to the correct registration. And actually we showed that actually, say you had like, 50 good possible initial correspondences that, in many cases, like 45 out of the 50 of them led to the correct registration. And if you didn't get to the correct registration, you just basically keep on going until you get to the registration that matches really well. And so we've got a nice paper on the whole pipeline of feature detection, registration, and then it's really important for 3D scans to verify that you've matched the scans properly. So it's actually surprisingly easy to get yourself into a situation like this, where if you look at the vast majority of the points, the matching error looks great, but actually you're off by some critical 3D transformation. So for example, this happens a lot when you're registering buildings, where you could be like, everything is good, but you're off by one window, right? You should be clicked over by one window, and it's hard to catch that error because there's only a small stripe of building where you can actually see where that error is. And there are also lots of things that you can do with exploiting the fact that you know where the scanner was. And so you can also use things like free space. And so let me just make a note about that here. So what I would say is exploiting free space. So the idea there is that it's not like you just have these 3D points sitting out there in the world. What you actually have is you've got some surface, and you know that I scanned the surface along these rays, right? And so then if you have some other scan like this, say this is scan number 2, and there's a chunk of scan out here, you can automatically say this is a bad registration, because if this surface had been here, I would have hit it, right, with my scanner. I would have seen something in that space, right? So, it's actually something that's worth thinking about, is not just thinking about these as sets of points, but also thinking about these things as sets of points that have clear free space along a ray from the scanner to that point, right? And we talked about that in our papers, about how you can make sure that you kind of exploit that. And so that's basically the idea behind scan-to-scan registration. You can also do the same thing with multiple scans. And so here's just a video of our VCC taken from I think this is 22 or 23 different perspectives. And you can see the different colors show the chunks of 3D points that contributed to each piece of the scan. And so this, as you can see, no single scan covers more than kind of a certain, piece of the surface. Whoops, come back. But we were able to kind of pull all these scans together into the same coordinate system. And actually, let me just say a word about that before I go on. So how does this multi-scan registration work? Well, in a way, it's kind of analogous to, it's kind of analogous to bundle adjustment in a way, right? So multi-scan fusion. Kind of what you can do is you can imagine that I have a bunch of 3D scans. Say I have 6 scans that I want to register, and what I can do is I can try and pairwise register each of them. And so you can imagine that what I make is kind of a set of edges in a graph where every edge represents a pairwise registration that I found. And then I try to simultaneously estimate all of these rotations and translations for each scan in 3D space in a way that minimizes all of the possible errors between all the scans, right? And so, when I have hundreds of scans, this may become a very difficult thing to do. But this is kind of the idea, is that I kind of have a graph of images, or a graph of scans. I have edges that represent possible correspondences between scans. And I try and either incrementally, like if I see a new guy, I may try and incrementally fuse him into the graph, or I may try and run some sort of like overall bundle adjustment at the end that brings all the scans together into the closest alignment that I can get. And some of these registration algorithms also apply equally well. So usually we want to register like LiDAR to LiDAR. It's also true that you can use similar ideas to register like LiDAR to structured light or LiDAR to multi-view stereo. But it's worth noting that the kind of qualitative nature of the points that you get is actually a lot different. Like the LiDAR scan points that you get are really different looking than the multi-view stereo scan points, or the multi-view stereo 3D points you might estimate. Like the LiDAR scan points are very regular, right? And the multi-view scan points are like kind of arbitrary, because like we talked about last time, this patch-based multi-view stereo is just kind of generating a bunch of random patches in the world. So comparing the two can be a little bit tricky. So it can work, but it's harder. And so kind of the last thing I want to talk about is, so once you've got all these scans in the same frame of reference, how do you kind of build the final mesh, right? So obviously, in many sorts of computer graphics applications, what I want to do is I want to take all these 3D points, and instead of having just a collection of points in the world, I want to have like a nice triangulated mesh, right? And kind of the first problem that you run into is that, if I have two original scans that overlap, how do I disambiguate all these triangles, right? So you could say, okay, what I could do is I could remove any triangles that are outside, that are fully inside. So here, say I want to register the black and the gray. So the first thing I do is I can say, okay, I'm going to remove any black triangles that are like fully inside the gray mesh. And then what I'm going to do is, in the overlap region, I'm going to generate some new vertices that were not in either scan and build some new triangles together that kind of sandwich these two scans together. So this would be kind of like what I would call a mesh zippering approach, right? So I basically have many triangles outside the seam that come from the original scans, but when I have two scans together, I kind of want to just kind of pick and choose triangles between them. One thing that you can see here is that, I end up introducing a lot of really weird skinny triangles in the overlap region, right? So this is not going to be a very friendly triangulation for doing subsequent stuff, right? So a better way to do it is, so there's this very famous algorithm by Curlis and Lavoie called VRIP, or Volumetric Range Image Processing. So let me write that down. So let's say multi-scan fusion. So there are a bunch of possibilities. One is called VRIP. This is Curlis and Lavoie. And the idea behind that was kind of a level set approach. And so we talked about this, let's see where it is here. We talked about this kind of a little bit last time in the context of multi-view stereo. So the idea is that, so I acquire a scan from one direction and I acquire a scan from another direction, okay? And so the red points are the actual original scan points. And then what I do is I say, okay, I imagine that the scan points are places where I have samples of a function in 3D where that function is 0, okay? So it's like saying I have samples of the 0 level set of a function. And then kind of what I do is I build a map of other places where that function is non-zero. And so in some sense, when I'm between the scanner and the original surface, then I say that that distance is negative. This is 0, and then the distance is positive over here. So it's basically like the distance is increasing as I push through the original scan. And so kind of what I'm doing is I'm saying that every scan produces kind of like this distance map that says, you know, what is the value of the function. And so here what I've got is a bunch of negative values of the function. Here what I've got is a bunch of 0 values. And here what I've got is a bunch of positive values. And then the yellow around here is basically saying that I only do this for a little narrow neighborhood around the scan. I'm not trying to extrapolate well beyond where the scan originally was. I'm only saying in the little neighborhood of my scan, I build this little distance function. And I do that for my other scans also. And then what I do is I basically try and fuse them together into a single new distance map. And then I look at the 0 level set of that distance map, and that gives me a new surface, right? So the idea is that, again, to make this work, I have to kind of voxelize up the space. And that may seem, again, like we're going to have a big problem. But one thing that is important to note here is that I'm only using a very small fraction of the voxels in this huge grid, right? I'm only using the ones that are really just near where the surface is. And so that's how you can avoid this kind of curse of a zillion voxels, is that I only look at exactly what's happening in a very narrow shell around the surfaces that I actually scanned, right? And so basically what you're doing to create this guy here is it's kind of just like a weighted combination of the original distance map. So it's like something, it's this times some weight plus this times some weight gives you this thing. And so to get back the red points on the merged scan, then you use an algorithm that's called something like isosurfacing. Like, have you guys seen marching cubes? Marching cubes is like a common graphics algorithm where you want to basically find the surface of an object from, you know, these volumetric measurements. And so, you know, that is one kind of straightforward approach, and lots of algorithms, lots of old algorithms used it. Another thing that you could use is basically kind of similar to the scatter data interpolation ideas that we talked about way back in chapter 5, I guess, right? So kind of an analogy to that in 3D is the following. So you'd say something like, okay, again, I have a set of samples that come from my original 3D points, right? And I assume that at those samples, at these black points, the value of the function is exactly 0, right? And then I say, okay, well, points that are slightly in front of that surface, say I'm going to give the function value -1 to all those points. And then function value, you know, points that are slightly behind the surface, I'm going to give +1 to all those points. And so basically, the idea is that every 3D point generates possibly like 3, you know, functional values, right? The one on the surface that's 0, one that's slightly in front that has a negative value, and one that's slightly behind that has a positive value. And then, let me just say, and then these kind of in front of and behind, what you're doing is you're kind of traveling along the normal to the surface is the idea. And then I just toss those into a functional approximation that says, okay, you know, I have a function of 3D, you know, space that is equal to some sum over all of the, you know, points where I had constraints. And again, I have some sort of a radial basis function and some sort of a linear part like this. And so this is kind of like a linear piece, and these here are like radial basis functions. And so you guys did this on one of the homeworks, right? This is exactly like the homework, except you're doing it with 3D samples, and instead of trying to estimate in the context of optical flow where the value of the function was the location of that point in the other image, the value of the function here is either basically 0, 1, or minus 1 for each of these things. And so, again, you form up a big matrix that has like lots of radial basis function values in it. You do a\b, and you get the value of the function's coefficients here, these guys. And then once you've got those, you can estimate the value of the function at any point in 3D space. And again, you use some sort of like isosurfacing Marching cubes algorithm to find that surface. Just one caveat is that when you're talking about like a LiDAR scan, you've got tens of thousands or hundreds of thousands of points, right? And so, unlike your homework problem, this becomes rapidly intractable to actually form up the matrix. Because if you remember, the matrix that you have to work with has like a whole bunch of phi functions up here, and there's basically one for every constraint. And so if I've got this having a dimension of millions, right, then suddenly MATLAB can't even handle all that data, and this is a dense matrix, so it's very difficult to do the backslash. So there have been a lot of kind of clever numerical approximations to the answer to this problem. So instead of actually forming up the literal distances, you have what are called near field and far field approximations. So like when you're really far away, when 2 points are really far away, you don't even bother to compute the radial basis function. When they're close together, that's called the near field. You have an approximation that maybe is easier to compute. So there have been some papers that I talk about in the book that make this computational process more tractable. So you wouldn't, even though the philosophy is the same as what we talked about in the CR data interpolation, the implementation of it is numerically much more clever. And the final way of possibly doing this is what's called Poisson surface reconstruction. And this is actually used a lot, partially because the authors have made it available to people to work with. And so this, again, is like kind of a callback to the Poisson stuff we did in Chapter 3, right? When you guys were doing the source to target merging, right? The idea here is that we imagine that the 3D surface, right, is like a boundary between a world where a functional value is 1 or 0 and a world where the functional value is 1. And so the idea is that the gradient of this function basically points in this direction, right? And in theory, this is like a step function, right? So I mean, if you think about looking at it from the side, basically what you have is a step function in the gradient. And so you can imagine that every 3D point that you get is like a sample of the gradient of a function. Everywhere in front of the surface, the gradient is 0. Everywhere behind the surface, the gradient is 0. Everywhere on the surface, the gradient is very large and it points in the direction of the normal, right? And so the idea is that now you treat this exactly like a Poisson problem, where you say, okay, now I've got a function where I know its gradient at a lot of places, and I want to go back and reconstruct an actual value of function that's consistent with all these gradients, right? And that's exactly what the Poisson surface reconstruction thing does. This is a better picture of it, right? So outside, the function is 0. Inside, the function is 1. On the boundary, the function has a gradient that points along the normal, and every point gives you a sample of that. And again, it's actually very similar to the Poisson reconstruction process that you guys looked at way back when in the compositing chapter. Okay, and so let me just conclude by saying that there are a lot of algorithms that you can kind of take that we learned about in 2 dimensions, just for images, and apply them to 3 dimensions. And so for a couple of my PhD students, we worked on those kinds of problems. And so let me just show you a couple of examples of that. So one example is kind of like segmentation, or finding an object, right? Finding a 3D object in the clutter of a 3D world, right? And so here's kind of a little video that shows trying to find windows in this VCC building, right? Where we kind of move this candidate along the surface, and when it coincides with the window, this kind of cost function spikes up. And so the idea is that you could try and use this to find objects that were kind of regularly occurring. So you can use this to find like cars in a parking lot or windows in a building, something like that. And again, the basis for comparison under the hood is going to be something like kind of like a registration cost function that says how well does the window match up to the surface at every point. And we also had some, again, a lot of free space reasoning about, in theory, not to make this too complicated, but in theory, if I put the window fully inside the building, right, there's nothing to prevent me from saying that's a good match, because there's nothing in the data set that contradicts that. It's like saying, okay, I hit the surface of the building before I could have seen the object I cared about here. And so in theory, that's fully consistent with the window being anywhere inside the surface, but it's a bad match because you don't have any evidence for or against it, right? And so there's kind of like two measures. One is kind of a measure of, you know, how well the surfaces match. Another one is kind of like how many of the points on the object that you've actually seen. So we call that consistency and confidence. Another one that was kind of clever was kind of like a graph cut version of segmentation, but in 3D. So this is like kind of 3D graph cut where we're segmenting out this 3D trash can. Even though we're stroking in the original image, we're actually segmenting the object in 3D, right? So this is like saying, you know, you're not only using the image boundaries, but you're also using the 3D depth boundaries to segment out 3D objects. Because again, if you were to look at this trash can in 3D, it's not a solid object at all. It's like a bunch of colored, you know, sparse points in the world. And so even though it looks easy to do in 2D, you know, it's harder to do in 3D. And finally, we made a 3D version of in-painting. And so here's the idea, is that we want to remove this mailbox from the scene, and so we're in-painting using kind of like a Cremonese-like algorithm, not only on the image, but also we're simultaneously filling in patches of 3D depth, right? So we actually fill in the entire 3D space. And so in the end, the image looks good, and the scene looks good, right? And so, you know, that was kind of like just almost a straight port of Cremonese type reasoning to 3D. So 3D in-painting, that was kind of fun. And so the idea behind this is that, you know, there are lots of times where you have holes in LiDAR scans, or you have thin objects and stuff like that that you need to remove. And so I think that's about it. So any questions? So like I said, this is one of the few parts of the book that I actually contributed something to research-wise. And so, you know, we did a lot of work, you know, several years ago on feature detection, registration, you know, this in-painting and segmentation stuff. A lot of this work was done in collaboration with Chuck Stewart at RPI, who you probably know from the CS side of things. And that's the reason that we bought our LiDAR scanner in the first place, was to do some of this research. And so you can go on my webpage and find old 3D papers. Okay, so no questions? So this is the last of the required lectures, and so for those of you listening at home, I hope you enjoyed it.